Hi, this is part 3 of the Wiley Spectral Webinar Series concerning AMDIS for processing EI mass spectral data files. This is actually done on my own personal computer. I want to post on a YouTube channel, so it'd be very similar, almost identical to the one I gave for the Wiley webinar presentation, but I'll just do it locally. So, my name is James Little. I'm from Kingsport, Tennessee, and you see my contact information in the slide. I'm a retired research fellow for Eastman Chemical Company. I did 42 years of experience on unknown identification. Now I'm a consultant for MS Interpretation Services, which is my own company, and so it's just one person in the company. I had a lot of different specialties that I used at Eastman Chemical Company, but they all really tied back into trying to do unknown identification by mass spectrometry or unknown identification problem solving in general. Eastman Chemical Company has 50 manufacturing sites, about 14,000 employees worldwide. I worked in Kingsport, Tennessee at the main location. But what was most important, we had about 50 mass specs networked worldwide so that we could share data and information with each other, get expertise from local people and for remote people. So it was a very good situation for using the NIST database for solving problems, the NIST library and the Wiley library and the NIST Search software for solving problems. This will be the third one in the series. We're going to do 5 of them. The first one was on spectral searches with the NIST MS Search. The second one was on structure searches with the same software. This one will be about AMDIS, a data processing program for processing EI mass spectral data files. The next one will be advanced NIST hybrid search, something relatively new within the NIST toolkit. And the last one will be creating and sharing user EI and MSMS databases, which even really include Wiley because they are really defined as users since it is the NIST software and they have their own library. The handouts for all the sessions are really important because I can't really discuss everything. This is just to give you an idea, and some of the settings are very detailed, and I don't want to go through them in detail in the presentation, but you can find all the handouts on my website, and I would encourage you to use them when you're trying to learn how to use the software, either on a second screen or print them out. But if you want to find them, you can look at my website that was on the first slide, or just type in little mass spec and saline. That should bring me to the top on the Google search. There are a lot of help files for the NIST search in general and AMDIS in particular, and you have them within the program, you have them within manuals that you can find on my website, the most current one, and you can also find them on help screens and also the pull-down menu that shows different programs that they have. So if you need help, look around. There's a lot of information on how to use the programs in general. The NIST software in general is Windows compliant. So all the commands that you might use, you'll find here, that plus a few different additional ones that might not be part of Windows. The thing that I like a lot in some of the programs, you can search by one attribute, let's say match, but then you can resort by reverse match without having to do a search again using those parameters. So that's very handy for sorting things. Well, what is AMDIS? AMDIS is an automated mass spectral deconvolution and identification system, but it wasn't developed really for users that wanted to do qualitative analysis, but that's what I will be talking about is qualitative analysis using AMDIS. But it was really developed to automatically detect chemicals in violation of chemical weapons conventions. What it does is it is software to separate, in a sense, deconvolute, separate the chemical noise from the GC mass spec component of interest so that you can get a good search for it to see if you have an identification. Deconvoluted spectra can be sent to the NIST mass spectral search program for identification externally, like we discussed in the first 2 sessions. But spectra can also be searched on automatically within AMDIS to give results yielding names, but not structures. But it's still a very valuable thing, and I'll show you how to do that also. And software can be used to automatically find targeted species. If you make up a small library or list of things that you want, that'll go into a complex mixture and show you if they're there or not. If necessary, you can do manual background subtraction, just like you would with a regular program, though its forte is really just doing deconvolution. But if you need be, you can do it yourself and see how it compares. And you can compare good and bad samples, which can be very handy for complex mixture to find components that were in the bad sample that weren't in the good, or vice versa. You can create retention indices using a calibration mixture for comparison to NIST values, because they can do a lot of searching or limiting of the search by retention indices, but AMDIS is what they use to calibrate your spectrum to attain the retention indices that you can use within the NIST search. So what are the AMDIS Essentials? Well, one thing you might find a little different from some programs that you can use to process data files is that you have to deconvolute before you send a spectrum to the library search. You can't just send it without deconvoluting, so always do that first. So you must always open the file and then run it. Always do that. 3 ways to obtain a spectrum for searching. You can do it automatically by running it, as we mentioned here, but you can do it also manually by left mouse button on a spectrum. Again, after you run, you can just single click on any chromatogram retention time and it'll give you the spectrum there, or manually where you get a background subtraction. AMDIS extracts the mass spec data of individual components from the chromatograms, and these are symbolized with a little triangle, a blue triangle on top of the chromatogram at the point of elution. And you just click on that with your left mouse button, and then you can step across the peaks that you've identified using your arrow keys on your keyboard. When AMDIS extracts the spectrum, that spectrum can either be automatically searched against an internal, that should be internal, not integral, AMDIS target compound library, or a commercial database. You can do it internally or externally, whatever one you want to do. But internally, it doesn't show you the structures. Externally, it goes to the NIST and you have all your structure display like normal. If a component is identified in these internal searches, a T is placed above the triangle to show that the component has been identified within the software, either targeted or within using a database such as the Wiley or the main library. So I want to show you some things about the AMDIS software. The majority of the presentation will be live. So I'm going to go out of this screen and get over to the AMDIS screen and share that with you. So the first thing I told you, before you look at a file, you have to open it. So I'm going to open an Agilent MSD file, and I'm not going to save the current results. And here's the raw data. It's come in, and you can see the chromatogram on the top, and you can see the spectrum on the bottom. If you click on one of the components with your left mouse button, you can see you get a spectrum. And to send it to the library search, you would just go NIST library, go to NIST MS program, and that would send it over for searching. But unfortunately, you can't, it's just the way it works. It's not really unfortunate, it's just the way it works. You cannot send something before you deconvolute. So after you open the file, just automatically run it. Doesn't matter what the settings are, just get something. Now when you get a spectrum, if you click on it, you'll see it in black on the bottom, and you can send it to the NIST library search. Go to NIST Mass Spec program. You can see it's automatically opened the Mass Spec program, and the results show up, the components at the top, and the results are at the bottom. That's some type of an aromatic amine. And so easy enough. To get back to it, just click on the return arrow, switch to at the top up here, goes right back to AMDIS again. All right, so that was to get a manual spectrum. Let's see what the deconvolution did. If we just click on the top here, and we'll go back. The first thing you should always do, because we really don't know how the settings are, is to go to the settings within the computer and see how they're set up. The tabs that you're most interested in are the deconvolution tab. And the best thing to do, since this really doesn't have saved settings, is just go to the default settings and say default. And then go over to the filter setting, turn and hit default there also. Now you're back to what would be the default parameters of the program. We'll say, do you want to run the program again? Yes, we need to deconvolute again. And this would be what it would standard display would come up. And if you click on one of the blue arrows at the top, you'll see you'll get a spectrum at the bottom, and you can search through or click through these. I'm using the down or up arrow buttons on my keypad on my keyboard to jump through them. And what you see on the bottom is wherever, when you're on, you've selected the little arrows. So when you're using the key, you're jumping through them. On the bottom, what you'll see is you'll have the mass spectrum of the deconvoluted, the background subtracted spectrum in white, and you'll see the uncorrected spectrum in black. So you kind of see this two-tone type spectrum that tells you what you've got. And normally if the black matches the white, it says it didn't really background subtract much of anything. But you can see there is a little error here, 2832, maybe a little argon at 40, but pretty clean. But if you come over to one of these other peaks over here, where it's a little noisier, you can see that the biggest peak in the spectrum is the 2832 for the air, and the smaller part is the white for the compound. But still, it deconvolutes it nice, and if you send it to the library, you should get a nice result for the deconvoluted. This is 2-ethylhexanoic acid, the unknown at the top, best hit at the bottom, just like we normally get in the NIST display. So a nice spectrum, nicely corrected. Let's talk about one thing that you really need to understand about this. The software tries to deconvolute things, and if it gets confused at all, whether peaks come together, if you look at the bottom down here, we have 200 and 201, and I'm going to left click and drag to blow it up like you would any data system. If you look closely, you'll see that the black is the unbackground subtracted, but the white is dotted arrows now. And those indicate uncertain peaks. And what I'm going to do on this system, if you click on a peak at the bottom, I've got it selected so it shows a color, and it automatically takes the ion current for 200 and plots it on the chromatogram above. And you can see 200 is showing here at this point in time. I'm also going to plot the 201. Now I'm going to blow it up. I'm going to left click and drag on the top and take a look at it. And the problem is these uncertain peaks are due to this peak shape for the 200 is different from the blue. And it really is probably not that significantly different, but the AMDIS program will try really hard to resolve components. So I'm probably resolving things better than really the data deserves to be resolved. So the other thing you can do here if you want to make these go away is just click on them and they magically disappear. If you want to see the 200 and 201 again, let's do that. And you want to see them without the white for the total ion chromatogram, you can make it go away, bring it back. But we need to make these, we need to make sure that it sees these uncertain peaks. And you really need to do that by right-clicking on the bottom and say, show uncertain peaks. You don't want to have that off. You want to have that on. You want to know if you have uncertain peaks. So have that on. And then the other thing you can say is view, find, add components, use uncertain peaks. You need to have this click. That means when you send that spectrum to the NIST library search, it will use those uncertain peaks and send them. If you don't have that selected, you'll get over to your spectrum that's being searched in the library and they won't be there. So you really need to have those there. So have that clicked. But if you do an internal search, which I'll show you later, it won't use uncertain peaks no matter what. So it's better to get rid of them. So let's go into our settings and see if we can get rid of them. Analysis, analyze, settings. And we're going to go down to the deconvolution. And these are the parameters that are real important. I want to set the resolution at low because I think it's really trying to resolve things that aren't there. And I want to send the shape requirements to low also. And when you do that, you have to reanalyze again. It says, yes, I'll do that. And we'll go back to the peak up here. And you'll see now that if you blow up the 200 and 201, then it's not trying to over-resolve things. And when you send that to the library search, it'll go. But if you unzoom, you'll notice it only did it over the area that's displayed on the screen. And that's a good thing, because sometimes if you want to work on a peak, you don't want to be doing the whole analysis over again where you're resolving everything. You just want to work on it. But after you get what you want, kind of clean up here, and then you just say run again. And when you do, it'll get rid of the uncertain peaks for all of them, and they're all cleaned up now. So if you want to see little peaks in the top one, again, like we said, you could plot 169 versus time. You could plot this 130 versus time if you wanted to, but you can see those peaks are pretty small there. So like I said, turn off the TIC, but the other thing you can do is take log scale for chromatogram. That makes the big peaks smaller and the little peaks more or easier to see. So the log scale is nice, but of course, if you look at a log scale on the chromatogram, it might not look, it'll look a little distorted sometimes, but that's handy things to do. But I'm going to set the log scale off. I'm going to turn off these ions. And so I've got everything. The only thing other that I've noticed about this file is there's a lot of small peaks. There's 45 components in here. I would just like to have the major peaks because I think the rest is probably just chemical noise or too small to be concerned with. So we need to look at our filter settings again. You go back to your settings. One thing you can do here if you want to, you can change the sensitivity from very high to very low. And that'll work on a lot of files, but sometimes the easiest thing to do is just go over here and say filter and say enable these filters. And these default ones that AMDIS picks are pretty good. So if I just use those, enable those filters there by turning that on and say save, it'll say, do you want to analyze again? I'll say, sure, that looks good. And now you can see I only have one component for every, one mark for every major peak. And I can step through those nicely and look at everything. This one it marked twice because it's such a broad peak, but all of them give me nice spectra. So we were successful in what we wanted to do there. So let's look at some of the other settings here. The one I like a lot is show mouse position on the cursor. I just like to see it on the cursor. So as I move around, I know what the retention time is, what the ions are. That's a good one to have selected. I like, if you go up to mode view, I like thick lines. If you put it on thin lines here or the standard, you can see they're harder to see. I like thick lines. If you turn off the color selected peaks and you do a selected ion chromatogram, I'm gonna click on 73 at the bottom. It takes 73 at the top, but you can see my 73 ion is not color coordinated with my extracted ion at 73. So I kind of like that to be on too. So I'm going to turn on color selected peaks and that'll keep them color coordinated. As I click this one, the blue will go with the blue, etc. So that's kind of a nice thing to do. So that's pretty easy to do. This middle chromatogram, really, that is really what ions that it tried to use to model where the peaks were. So it kind of plots, this is all automatic, and you could make this window go away, but I like to see that it's working properly, so I just leave it on, just because it's such a central part of the program. So that's pretty much the whole Windows display here. And always right-click on things to unzoom. There's some other things, but the main thing I was told you is make sure show uncertain peaks is marked. Make sure view uncertain peaks is used in the library when it goes over there, when it analyzes things. You need to use uncertain peaks. So those are the key parameters. And then once again, the settings is a very important thing. All right, so let's go on and get us another file here. I'm going to open another file. This one I'm gonna have to change. This is not a Agilent one. It's actually a netcdf file, a standard converted file from another vendor, from one vendor to a standard format. And it's called Big, and I'm gonna open it. And I don't want to keep the data. You could if you wanted to, if you don't want to start over again. I'm going to just delete what I just got through working on. It didn't delete the file, it just deleted the deconvoluted results. If you look at this file, see that things look pretty bad. The peaks are over very wide, rugged looking on the top. But again, like I need to deconvolute before I can really work on anything. So I'm just going to pick a peak and narrow it down so it doesn't take so long. I could have just done the whole file, but it would have worked on this big peak over here and taken a long time. What I really want to do, can I get a good spectrum of this? Well, I showed you one way. We're just going to expand it a little bit in the top. If I just single click at the bottom, you'll see I get a good spectrum there. But if I go to the top of it, you'll see that all the peaks appear to be saturated. Like the peak here for the 257 was small. Here, the 257 is probably saturated, and the little isotope peaks continue to grow. So a very distorted spectrum that you wouldn't want to try to do a library search on. So I can look at the back and see if it's the same as there. But if you plot one of these ions like 257, you'll see it's flat top in the top up here. Let's make the total ion go away. It's totally saturated. If I plot one of its isotopes, maybe at 259, you can see it's not saturated. So if I get one on the front side before the big peaks get saturated, I can get a good spectrum and get results from it, even though it's way too much injected on the column. So I'm gonna go to the front. Let's plot the 188 ion because it's big. And I need to get someplace where it's just not saturated. So in this region I should get a good spectrum right there. So that's actually a good spectrum, the compound. And you could send that to the library search if you wanted to, and you get a fine result for it. But what happened you had some chemical background that you wanted to get rid of also. This is the third way you can get a spectrum. Go to Analysis, and Mode, we want to go to Manual. All right, when you go to Manual Mode, when you right-click on the top window, you will see that there are other things like background and signal that you can do background subtraction. But to do those background subtraction, you have to turn manual on. And that's a little different than some data systems. So you got to do two things to get a manual spectrum. But they did that so that they can still do the unzoom. They would be grayed out if you're in the manual mode. So I'm going to the manual mode. Now I've got a little arrow that shows me where I'm going to take my positive signal for the sample. So you see it doesn't look saturated there. But then I can come over here and say background, and I can get a background for it. And what it's done now is taken a spectrum such that it took out the background, the 207 silicon peaks, and gave me a good spectrum for the spectrum here. So I have a background here, real signal here. If I go and send that to the libraries for searching, I should get a good spectrum. It's actually a silation reagent. It's a trifluoroacid-amide, one of your silation reagents. So now I can get a good spectrum. If you want to clean this up and go back to where you were, you probably want to turn manual off. You want to unzoom to get back where you want to. I'm going to get rid of this extracted ion. The other thing, before I forget that I did it, I'm going to go up here in mode and put it back in component mode. So if I blow it up now, you can see I still have my peaks marked that I had. But that's a good way to get a good spectrum of a saturated peak. And you need to be careful. Plot your ions for big peaks and make sure the spectrum is not saturated. Take a little spectrum on the front, one on the back, compare it to the top, make sure you get a good spectrum and make sure it's not saturated. But if you do good chromatography and don't overload the system, then you shouldn't have to worry about saturation, but you can get around it with this manual mode. So that's pretty much on how you do a background subtraction. Now I want to go and do a little bit more complex analysis, showing you a little bit more complex file. So I'm going to open another file. And I'm going to go File, Open. I've got another file that's kind of interesting here. It's Grow, but I think it comes with the AMDIS software as a demo file if you want to play with it. Go to delete what I have because I'm not going to bother keeping it. Now you can see you got a pretty complex mixture, relatively speaking, versus the other two files. So of course, like we always did, let's just go before we run it. Let's just look at our settings. Let's reset our settings to default. Make sure we know where we're at. Let's do a default here. So everything's good again. And save. Hope there's not any uncertain peaks. I don't think this file is better quality, so I didn't have trouble with uncertain peaks. But you could leave the uncertain peaks on. Those two sensitivity settings if you wanted to that we talked about, the peak shape and the resolution, but we're not for here. So now we're going to run it and see what we get. All right, we got 90 components. That's pretty complicated. If you wanted to even see more, you go to Analysis or Analyze Settings, go to Resolution, go to Sensitivity, and let's put it at high, very high. Let's just go as high as it'll look for everything it can find. It'll say, do you want to analyze again? Say yes. See, it's taking longer now because we're really pushing the programs to its limit. Remember that we had 90 components here. Let's see what we get here. It's taking a while. And almost 80% through, 94 or 98. Okay, now we're up to 539 components. That's more than I want to look at for, let's say, for this analysis. So let's go set our settings back to sensitivity, just medium, which are the default settings, and say save. I think 90 is plenty. I don't think we need to look for any more. All right, so we got our 90 components. That's still a lot. So let's just say we don't want to look at some of the smaller components. So let's pick this one. Let's just say this one is too small. I click on the little blue arrow, and if you look over in this right pane that we haven't talked about, it gives you information about the model that it used. But what I want to look at is the signal to noise total is 56. So I think I might want to not look at anything that's bigger than a signal to noise of 200, and this peak will definitely go away. So let's unzoom and go up to our settings. Now Analyze, Settings, come over to Filter. We're going to enable the filters, but instead of just using the standard filter settings, we're going to click Exclude If Below. So we're going to put Exclude If Below. Let's just put in 200 and say save. We had 90 components before. Let's see what we got now. Now we're down to 15 components. So it's just got primarily the major components in the mixture. So that's not bad. That's what I want to show you with will work a little bit better there. So what I want to do now is to get library searches of every component within this program. I won't get structures, but I'll get names. So you have to come up here. You have to first deconvolute, Then you go up to Analyze Mode, see, Search NIST Library. But this means search NIST library within the program, not outside. So I'm going to tell it to search the main library here. You could tell it to search any ones you wanted to or any combination of them, but I'm just going to do the main lib for now. Maximum number of hits per component, 10. That's all okay. So I'm just going to say analyze. And you can see it's searching all of those. So I'm going to say keep because I want the results from this. I want to look at them. And now you can see our little T's above. That means that everything with the T above it has been selected. So if I click on a T to highlight it, click on the last one here, you can step through it with the arrow keys. There's a bug right now that's better to step through them from reverse order than forward, but I'm stepping through them. So you can look over here, you can see the identity. So that's a hydrocarbon, that's a hydrocarbon, that's a hydrocarbon. Let's say you didn't know what ecosane is. You can right click on it, right here on the retention time and say NIST library, go to NIST program. And it'll send it over to the other NIST program and it'll tell you what the structure is. So this is a long chain hydrocarbon molecular weight 282. So it's got a lot of hydrocarbons in it. If you can't see all these, sometimes it's better to go over here to the view and say undock. That makes this little window come loose. It actually jumped to my second screen. Pull it over here and now you can stretch it so you can see things better. If you want to expand, see what the other hits are, I can click on here. You can just step up through them if you want to. And so I'm just stepping up through the best hits. Okay, what we're seeing on the bottom is as we step through, at the top you can see we're jumping across the T's. But what we have at the bottom here is just like before. The black is the raw data, the white is the deconvoluted spectrum. But on the bottom, we have the best library fit matched against the deconvoluted spectrum, and you can see they match really well. So this is a good fit for it, and you can just step through them all. Essentially, you got everything identified very quickly. So it's a very easy way to qualitatively analyze things. You can actually send reports out to customers with just names on it. So if you just got something that's simple, or you want to look at a complex mixture really quickly and see what might be in it, I find it very useful to do that. It's actually working in both directions now. Sometimes it gets hung up, it's a bug. All right, so that's good. So we've found a way to identify everything. But the other thing is I find it really handy. Let's redock our friend here to get him out of the way. So view, undock, and it just makes him jump over where he should be. Made him small again. So what I want to do here is I want to see where things come. So you have to trust me here. I'm going to go to the components. Instead of being on the T, I'm going to click on the little triangle. So I just go to the deconvoluted spectra. This is a hydrocarbon, so one of its characteristic peaks is 85. So I can plot 85 really quickly. Kind of hard to see it with the TIC overlaid, so I'm going to turn the TIC off for now so it goes away. You can see there's a lot of hydrocarbons in this mixture, things with hydrocarbon chains. The other ion that's very characteristic of things in here is 74, and that's for esters. And you can see there's 3 esters in here with your hydrocarbons. I noticed when I was running this column has some problems, or the septa does or something, so there's a lot of silicon bleed. 147 is a very common silicon bleed peak, or maybe 73 for silicon, a trimethyl silo group. So you can see, let's just use the 73, it's a little bigger ion. So you can see you got big peaks are the hydrocarbons, the neck larges are probably esters, methyl esters of some type. Some other components that are neither of one, probably from the TIC if we bring it back. There's a lot of things that are not part of that. So you can easily see that if you want to see the silicon a little bit better, again, go to the log scale, and it kind of makes them easier to see in the presence of the major components. Let's turn that back off again. So that's a pretty easy way to decide really quickly what type of components might be in your mixture using these extracted ion current profiles or these selected ion chromatograms. So let's turn those off. Let's go back to the TIC to kind of straighten these things out. I'm going to unzoom the bottom because I kind of expanded it. Now we're back to the standard display. You can see where the ions optimize in the middle. So what I want to do now is do it even a different way. I want to say, I want to go to the NIST library and create a list of compounds that I'm interested in. So I found 4 that I thought I might be interested in these type of files, and I created a little list of them. So I created my own pseudo library, or a list if you want to call it. And to do that, you go to Analyze Settings, and the instructions are in the in the handout, so you need to look there if you want to find the details of it. I'm going to go to the default there to get that. Like we said, always go back to the default if you have any doubt that you might not be in some setting that you like. So I've done that, and then I'm going to pick a library. And to do that, I'm going to select a new library. This is going to be my target library. I'm going to do it, I called them JL Grove components. I created a little library of that, and I said open. Now that's my library. And now when I run that, we'll say save. It says, okay, if you save it, you changed it, you got to run it again. So run it. And you'll see it marks 93 components, but what it does, it goes through every spectrum at every scan, even the background scan, and looks for your spectrum. Anywhere it finds the target, it puts a T. So there's one of my T's, and these are my T compounds over here, the ones, the target I put a library of 2,6-dimethylphenol, 2-ethylhexanoic acid, and 2,6-dimethylaniline, and the butylated hydroxytoluene, BHT. You can see it found all 4 components, and when it did, it put a T on them. So I can quickly decide in a mixture of 93 or so components where they come. So this is a target library. So I've shown you 3 different ways to do identifications. You can send them to the NIST library externally where you get structures. You can create a file and search the NIST library automatically, or the Wiley library, or any library, or both of them if you want to, and create a list of the best hits internally. It'll put a T over the top of them. Or you can create your own small custom library or list of compounds, and it'll quickly target them for you and show you they're in with the T for the file. So we've got a lot of different ways we can do things there, but that's essentially the essence of AMDIS. It'll do a lot more things. It'll do internal standards. It'll do determine retention indices with external calibration using hydrocarbon boiling point mixtures. It'll do a lot of different things. But this is the main things that I've found useful for qualitative analysis. So that's what I wanted to show you today. So let's go back and finish up by going to the PowerPoint. I'm through with the live demonstration. Let's go to the other one. So we're done with that. The other thing I was talking about is comparing 2 chromatograms for differences. 2 data files can be compared to determine differences. I like to call it good versus the bad. Customers come in all of the time and want to know, well, this sample performs well, this one doesn't. Can you tell me a difference? And so this is the good versus the bad. And this is described real well in the manual and also in the class handout. But what you essentially do is you plot one of the spectra, the good or the bad, in one window, and then you bring up another chromatogram of the bad component, and you have them both at the same time. You deconvolute both of them separately using the same filter. You want to use the same filter setting since whatever you find is appropriate, use them for both. But when you get through, you're able to post-process things. And there's a post-process button. And when you do that, you can do the pull-down menu. And it'll show you the targets that you might have put in there. It'll show you things that match. It'll show you the significant things that are unique in all classes. So the significant things would be things that are in one sample that aren't in the other. And it quickly steps you through them by the T. You don't have to look at all 100 components of things that are the same in both, because it compared all the spectra for you one by one and told you they're the same, but these are the unique things. These are the things that are different. So if you have a very complex file, they can be very valuable for comparing things. And you can only I do one at a time. So good versus the bad. Retention indices I talked about. The new NIST software has a lot of methods in it. They have all the different methods with the different columns they use to determine retention indices for things. And there's a link to COVAT's retention indices at the bottom if you want to learn more about them in Wiki. But the NIST libraries have these indices for a lot of the compounds they're acquiring new. They run them such that they get a retention indices. What the program does, AMDIS allows you to convert retention times, which is system dependent, into system independent constants using a hydrocarbon calibration mixture. So they run a set of hydrocarbons that differ by 28, 14, whatever, and then calibrate your file against this calibration mixture using the formula for retention indices. And this creates a limit the search. So it actually creates a system independent. It's a dimensionless value, but it uses it to identify things. So you can restrict the retention indices to a certain limits. You can compare yours to the same compound, and it's really just an orthogonal way to get more information about the compound of interest to you and tell you if it's what it is, or if it's just an isomer of it maybe. And also the MS Search results list methods and conditions for all these determinations. And there's a way to set up the parameters such that it doesn't slow down things showing these methods if you don't want to. But again, that's in the handout for more detail. If you want to do your own retention indices and compare them to either the actual ones in NIST or the experimentally are ones determined by artificial intelligence by the ones that are calculated, and also Wiley calculates retention indices, and you can compare it to their theoretical and see if it is another support for the identification of your compound. As we said before, the webinar references are here. Everyone has a link to the internet. So I have my resource website, I've got manuals, there's all kinds of information on different ways to identify compounds here. So I hope you'll find those useful on my website. It also contains links to other people's websites also. So acknowledgements, even though this was done on my personal computer, I had a lot of help in learning how to do a lot of the things for webinar production by using the people at Wiley. They've been very gracious. Ryan and Kristen, I want to mention them. Thank you so much for encouraging me to do this series, because I hope I had a lot of fun doing. I've learned a lot myself, and I hope other people will find it useful. AMDIS technical advice, Gary Mallard is the expert by far, the world's expert as far as I know in AMDIS, and he works for NIST, and he also has his own consulting company. David Sparkman helped me a lot in some of the software and also figuring out some of the bugs we had in the initial production of the webinars. David is a mass spectrometrist at the University of Pacific professor. He's also a consultant in his own company, works for Wiley and NIST, and he offers many good educational classes on mass spectral interpretation if you want to learn how to interpret spectra better. And Stephen Stein, who's the head of NIST and behind all of these nice tools that they have given us, he makes things happen with his very talented team. So thank you so much for your time. And I really just want to say in conclusion that I think you'll find AMDIS very useful for processing complex files and simple files, because it just does such a good job of deconvoluting things that you can't background subtract yourself. But you know, you can still use your regular software if you want to, but it's a real valuable tool, and it's very interactive with the NIST search, and it does its own internal searches that are very, very fast if you just want to survey things quickly and not send everything out manually to the NIST search. So thank you for your time. Go out and visit my website, and I hope you'll come and hear one of the other 5 things that we talk about in relationship to this series. So thank you so much.